Hello class, today we're going to talk about lesson 15, which is on quadratic functions. Alright, and we've already talked a little bit about quadratics in the equation form. That's where we had ax squared plus bx plus c is equal to 0. And now all we're doing is moving that to the realm of functions with an f of x is equal to ax squared plus bx plus c. And actually, we are going to move this into a different form of talking about quadratics. There's still this form, right, which is still used, okay, but then we also have this other form. So this would, I guess, just be called standard form here, or ax squared plus bx plus c form. We also have what you would call a times x minus, say, h squared plus k. Okay, so let's talk a little bit about what this form is, what it's called, and what good it is. Okay, so our normal quadratic, our basic quadratic, the simplest quadratic we have is just x squared. Okay, x squared looks like this. It's a u. Okay, it's a u. Now, this form with the a, well, a would be 1 here in this particular case, and this minus h plus k, that would be something like, imagine, let a be 1. Okay. And then imagine something like x minus 2 all squared plus 3. Okay, well, remember from the last section, we're going to use that idea a little bit, that minus 2 on the inside of x squared. So if this is f of x, this would be f of x minus 2 on the inside plus 3 on the outside. So that's going to shift this function over 2 units, right, to 2. So minus 2 on the inside shifts to the right 2, and plus 3 on the outside shifts up 3. So we will shift 1, 2, 3 up, and it looks like we're right back on our graph. But yeah, what we're going to do is shift that parabola up. Okay, so we will have this parabola here. So the parabola in red is going to be this x minus 2 squared plus 3. And this point right here, where the parabola starts, that is the point 2, 3. Okay, we call this point the vertex of a parabola. Okay, it's where the parabola begins. It's where the u opens. Okay, so having quadratics in this form here, this a times an x minus h plus k, this is called vertex form. Okay, and the vertex is going to be h comma k. Okay, we could use other letters besides h and k, but I didn't want to use a's, b's, and c's since we have that here. But the a is the same, no matter which form you're going with. Okay, so this particular form gives us the vertex. All right, so for example, let's look at another one. Okay. So here is another example. Say we have f of x is equal to 2 times x minus 1 all squared minus 4. So if you remember, the formula we had was a times x minus h squared plus k. Right, so that meant when we go to the vertex is always hk. So we change the sign of the x-coordinate and we leave the sign of the y-coordinate alone. So we change the sign for x and we leave it alone for y. Okay, so it stays the same. For y. All right. Okay, so now I'm going to go through my minus h. Will have minus 1, so my vertex. Remember my x, I changed the sign. Right, we go from negative h to h. So negative 1 to 1, I changed the sign, but my y stays the same. So I have the vertex being 1, negative 4. Okay, so if I wanted to graph this, the nice thing about having the vertex, if I needed to graph this, I'd go out over to 1 and down to negative 4. 2, 3, 4. And I know that my parabola is going to open from this point. Now, if I want to know how it opens, well, one thing we can always do is plug in another value to get another point. In fact, that's pretty helpful to do that. So let's try 0. Plugging in 0 is always nice. So if I plug in 0, I'd get 2 times 0 minus 1 squared minus 4. Well, 0 minus 1, that's negative 1. So I have 2 times the negative 1 squared minus 4. Well, negative 1 squared is 1. So we'll have 2 times 1 minus 4. So we get 2 minus 4, which is negative 2. So here's negative 4. Here's 1. Negative 2 is here. So to graph this parabola, it's going to look something like this. So plugging in the, or getting the next point actually helped me figure out which way this function, this parabola was opening. We are opening up from the vertex. All right, so 1, 4 is the vertex. Okay, so the natural question might be, what's so good about a vertex, right? I mean, big deal. We found the vertex. What is it? Why is it good? Well, first of all, like I said, it's the opening point of your quadratic, but quadratics either make u's that point upwards, or they make u's that point or open down. And depending on which one you have, the vertex is either going to be your maximum or your minimum. Right? So in this case, the vertex corresponds with the minimum value of the graph. So the vertex is also equivalent to the minimum of the graph. All right? So the vertex is equivalent to the min or max, depending on which one you have. Okay? And you get a min for a quadratic that opens upwards with a u, and you'll get a max with a quadratic that opens downwards with an upside down u. Okay. Also, we have what is called the axis of symmetry. So the thing about quadratics, they make a u, but they are also mirror images of one another across this line. And this line here is x equals 1. In fact, it is the x-coordinate of the vertex. So the x-coordinate, I'll write this over here, the x-coordinate of the vertex is the axis of symmetry, or I'll say gives the axis of symmetry. Okay. All right, and how we list that is just as x equals 1 in this case. All right, and that just tells us what line the quadratic is mirrored around. right? What it's reflective around. Just x squared, it's reflective around the y-axis, or where x is equal to 0. In this case, it's x equals 1. Further, every quadratic has domain. Okay, let me write that. So every quadratic function has domain negative infinity to infinity, right? Because if you think about it, our original version of a quadratic, if I go back to my first page, is ax squared plus bx plus c. There's nothing there that will mess up x, right? We're not dividing by x. We don't have x's in the denominator. We don't have x's underneath the square root. All we have are nice powers and sums of x. So there's nothing that's going to mess things up. Meaning that the domain of every quadratic is going to be negative infinity to infinity. But on the other hand, the range, okay, the range goes from the vertex either up, right? So this quadratic opens up. So we go from the vertex, and I realized just now that I forgot to put a -4 here for this point. Sorry about that. It should be -4. So the range goes from the vertex either up to positive infinity if we are opening upwards, or we go from the vertex down to negative infinity if we're talking about the range. Okay, so the vertex also, while it gives us the axis of symmetry, it also gives us, and it gives us whether we have a max or a min, okay? It also gives us the range, because the range now I can say goes from -4 on up to infinity. Okay, so over here I can write that, the range, and this one's a little cluttered. Hopefully the next one won't be. But the range is, and I need to include that -4, it's going to be -4 to infinity. Okay, and if you open downwards, it's negative infinity up to whatever the y value is. Okay? All right, let's look at another example. Okay. For this one, we're going to let f of x be equal to -3 times x plus 2, all squared, plus 1. So the vertex, so remember, when we grab our x-coordinate, we change the sign. So for my h, I always change the sign. For my y, when I grab the y, I leave it alone. So the vertex is the point -2, 1. Okay, so let's graph this. I'm going to just plot my vertex right now. So -2, 1. So I'm going to go over to -2 and up 1. Okay, and now I need to find whether or not I'm opening upwards or downwards. So a couple ways we could do this. We could plug in 0, or just plug in any other x value and see what we get. I like to plug in 0 when I can. 0 is always a nice value to plug in. So let's plug in 0. And actually, I think I'll do it over here, up out of the way from everything else. But we'll plug in 0. I'll get -3 times 0 plus 2 all squared plus 1. Okay, so then we'll get -3 times 2 squared plus 1. So this is -3 times 4 plus 1. So this is -12 plus 1. So we get -11. All right, so that's way, way, way down there. Okay, that's, if this is -2, -11, well, here I am at -4. I have a long way to go. So maybe I should plug in -1 instead to get a better point that's not completely off my graph. -1 would be right here, and it would hopefully be around in my range. I could go all the way down to -11 if I wanted to, but if this is -4, that's going to be maybe all the way down here. So I want something a little more manageable. what I'm trying to show with this is just because I picked a value that's not on my graph doesn't mean I give up. It just means I pick a better value. Okay, so let's do -1. If I plug in -1, okay, I get -3 times -1 plus 2, that all squared plus 1. So -3 times, now this will just be 1 squared. All right, and the math is already looking better, right? Because that 1 squared will just be 1. I get a -3 plus 1, we get -2. So we get, when x is equal to -1, y is -2. So we can go down to -2. Okay, so that means we open downwards. And since we have this axis of symmetry, I also know another point, because this, since this has to be symmetric across this line, so this is the axis of symmetry here, often abbreviated as AOS, the axis of symmetry, that means here, okay, this is -1, at -3, when I go 1 away from the vertex in this direction, I have to go down to -2 here as well. So it has to match on both sides, right? So that automatically helps us find where we are at -3. Okay, so the vertex is -2, the axis of symmetry is x equals -2. Okay, this is a maximum, so the maximum is this point. We could say it's the point, or we could say another way it's sometimes said is the maximum is 1 and occurs at -2. So I'll write that another way to say that, if the maximum is 1 and occurs at x equals -2. Okay, so we get a lot of information just from the vertex, but also finding that other point, that second point, told me not only where these other 2 points were, but also that the parabola was opening downwards. Now, what was the difference between the last example we looked at? So the last example we looked at, we were opening upwards. In this example, we're opening downwards. Well, it's actually RA. This value here, right out front, tells us whether or not the parabola is opening upwards or downwards. Okay, so essentially, if A is positive, okay, we get a U, okay, opening upwards. If A is negative, we get the frowning face, right? Now that, okay, that positive smiling, negative frowning, right? And that comes straight from whether we have a positive or negative out front here. Okay. Now, it's still good to find that extra point if you're graphing, just to get an idea of how this vertical stretching behaves. But okay, that's that. Then, now, finally, if I want to find the domain, well, the domain, remember, for all quadratics is -infinity to infinity. No problem there. The range, though, okay, the range, well, we go to our vertex, and it's always the y of our vertex, in this case, which is 1, and in this case, since we're opening downwards, we're going from -infinity up to 1. So the range is -infinity to 1. So that's a lot of information we get just from this form here. Okay, that raises a question then. If that vertex form, right, this vertex form is so useful, right? It tells us the vertex, it tells us the axis of symmetry, the maximum or minimum depending on what's happening, whether it's opening upwards or downwards, what the range is, okay? How to quickly graph it. What happens if instead we're given a quadratic in this form? This is just our ax squared plus bx plus c, okay, in our standard form. What do we do when we're given problems in this form? Well, I'll show you. Essentially, it's the same a, all right? A is the same. So our a here is 3, which is positive, so that must mean we have a u, right? We're opening upwards. And we can tell a lot from that right there. We have a minimum instead of a maximum, okay? But that's about it, all right? So we need to find a way to get from this form to the vertex form, all right? So we have some formulas that will help us out with that, okay? So let me show you those. Okay, so here's the formula. If you have ax squared plus bx plus c, now you can always complete the square to get this. Okay, you can always complete the square, which is a topic for another day. I think we'll get into that eventually. But for right now, what we're going to do is I'll just give you the formulas for the vertex. So remember, we have an h and we have a k. So h is going to be negative b over 2a. Okay? So that's our h formula for the vertex. Okay? And our k, the y coordinate, is going to be c minus b squared over 4a. So they're very sort of familiar, or kind of similar formulas. In fact, this negative b over 2a, that should look familiar, because remember, when you solve a quadratic equation, you get x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This negative b over 2a, that is the vertex. That's where that's coming from. And this plus or minus this thing over 2a, well, what's happening there is if you have, say you have a quadratic, here's the vertex, right, and it's going to be at negative b over 2a, and plus or minus where the quadratic hits the x-axis is where it's equal to 0, right? That's where the quadratic itself is equal to 0, and we're adding and subtracting that same thing on each side to get to that value. So it's the vertex axis of symmetry plus something and minus something, and it's plus or minus that same something, right? So that's where anyway, that's where this comes from. It's negative b all over 2a. The k, there are a couple ways to get that. You can either plug this value in to the function and get that, or you could just complete the square, and this comes from completing the square. So anyway, we're going to use these two formulas here for this problem. Let's go ahead and find our h. Our h is negative b over 2a, so b is 12, and 2a is going to be 2 times 3, which is 6, so we get negative 12 over 6, which is going to be a negative 2. Alright. Now, to find our k, k is going to be c minus b squared over 4a. So c here, c is our negative 2, so it's negative 2, minus, now b squared, b is 12, so that's going to be 144 over 4 times a, in this case that's 3. Okay, so we get 144 over 12, so this is negative 2 minus 144 over 12, so this is negative 2 minus 12, so our k is negative 14. Okay. So our vertex is going to be negative 2, negative 14. Alright, so here's our h and k. Now if we want to rewrite this guy in vertex form, we can do that. Remember, the a is the same, so the a is still 3. Then it's going to be x minus the h, which is negative 2, all squared, then plus the k, so plus a negative 14. Right, I put it in there like this so I wouldn't forget that this is going to be an x plus 2 squared minus 14. Alright. And as I've said, the nice thing about the vertex is we also get the axis of symmetry. Okay, so, and we already know where the minimum's going to be. I know from A that it's opening upwards. We already talked about that. There are a lot of things we already know. So let's graph this function. I'll do that over here. So since I have to go all the way to 14, I'm going to let my tick marks go in 2s. Okay, so my vertex was negative 2, negative 14. Okay, so negative 2, I'll make that negative 2, and then 2, 3, 4. Since these are going by 2s, 2, 4, 6, 8, 10, 12, 14, so that'll be negative 14 there. Alright, so there's where my vertex lives. Okay. I also know that this function's opening up, so I know that it is a u, but also, here's a really nice thing about standard form. Okay, these two, remember these two functions are the same, they're just in different forms, but if I plug 0 in, it's so much easier to plug into this version. So let me do that here. If I plug in 0, it's going to be 3 times 0 squared plus 12 times 0 minus 2, and all this stuff goes away and we get f of 0 equals 2. So the nice thing about standard form is that c is the y-intercept. Yeah? So the y-intercept we found is negative 2, that's our c value, so we know our y-intercept must be here. Okay? We also found that when we plugged in 0. So we have a very narrow quadratic here. Right? So it looks something like this, it looks like. Very narrow. At least on the way I've done it. So the axis of symmetry is x is equal to negative 2. Now be careful about that. Remember that comes straight from your x value in the vertex. careful about that. It may fuss at you on how you write that down. It's a line, x equals -2, not just the number -2. So, you know, be wary of that. Now, what else do we have? We know the domain is -infinity to infinity. That's true of all quadratics. And we know that the range, okay, well, since we're opening up, the range is going from -14 up to infinity. All right, so the range is going to be -14 to positive infinity. And we got that also from the vertex. We also know that this is a minimum. Right, so the minimum is -14 and occurs at x equals -2. Okay, so we have gotten a lot of information about this quadratic here. Okay. Alright, let me show you all another example where we need to convert and use these formulas. Okay, so I'll show these formulas again. H is -b over 2a, k is c minus b squared over 4a. Okay, here's another example. This one, -2x squared plus, or minus 8x plus 3. So already my a is negative, so I know we're opening downwards. We have a maximum. That's something we can see just by looking at this. Now let's find the vertex. Alright, so H is -b over 2a. Okay, so we'll leave the negative on the outside, but b is -8, and then 2 times a is a -2. So we have a lot of negative signs floating around here. So let's just be careful. These on the fraction will cancel, and then I'll still have this one on the outside here. So what I have now is -8 over 4. So we get -2. Again, it won't always be that way. Okay, you won't always get -2. It just kind of happened that way this time. And then our k is c minus b squared over 4a. So our c is 3. b squared, that's going to be -8 squared, so that's going to be 64. And maybe I should write that out a little more carefully so that you see I am putting the negative in, but since I'm squaring it, it goes away. Okay, and then this will be over 4 times a, which is a -2. Alright, so we get a 3 minus, we'll have a 64 on top, and a -8 on the bottom. Alright, so that's going to come out to be, well, a -8, but this negative and this negative cancel, so we get a 3 plus 8. Alright, and we get, now our k is 11. Alright, so these numbers have come out to be kind of large, but that's alright. So now our vertex is -2, 11. Right. So when we go to put that in vertex form, right, f of x has the same a, but now remember you change the sign. So you change the sign when you move it in. So it's going to be x plus 2 squared plus 11. Okay, in vertex form. Alright, so -2, 11. This graph is going to be interesting. here's -2, 11. Okay, so there's our vertex. We also have our axis of symmetry that I can already tell you what it is. Okay, it's x equals -2. And I can find my next point too, because C, if I go all the way back to my original thing, that's something I could have mentioned here, that the y-intercept is 3. Okay, 1, 2, 3, so we know we're going to hit that point here, and then, so I'm a 2 away. I also know, because of symmetry, that I have to hit 3 here. So this guy opens downwards like this. And you didn't see any of that. Sorry. Okay. So here's the y-intercept, and here, because of symmetry, we get this point. Okay. Right, so the axis of symmetry is -2, or x is equal to -2. We also have a maximum. So the maximum of 11 at x equals -2. We have that the domain is -infinity to infinity, and then the range, well, in this case, since we're opening downwards, we have this downward facing u, it's going to go from -infinity up to 11. Okay, so our range is -infinity to 11, and I'll close the bracket. Okay. And that is basically it, except if we wanted, one last thing we could probably talk about is quadratics always go from, say, increasing to decreasing, which makes sense since they have a maximum or a minimum. So they always go from one to the other, either increasing to decreasing, decreasing to increasing, something like that. And that is pretty much that for what we want to talk about today with quadratics. It's just going back and forth from these two forms. I guess I should say, if you want to go from a vertex form to standard form, which, you know, does happen, if you want to go back to this form, what you would do is you would multiply this out. You'd FOIL this out. So let me show you. You'd FOIL this out, so that's x plus 2 times x plus 2, so that's x squared plus 4x plus 4. And then if you distribute that -2 and simplify, you should get down to this. And I shouldn't say you should, you will get back down to your standard form version. Okay? And you can see it, the -2 times x squared gives you -2x squared. The -2 times 4x gives you -8x. And then the -2 times the 4 will give you -8. And -8 plus 11 will get you back to 3. Okay? Alright, that's that for quadratics, so I will talk to you all next time. Cheers.